And today we are looking at the last unit of energy and change. Okay, remember term 3 we said we're going to cover energy and change, and we are going to cover 4 units. We have already done the first 3 units, which were on electricity. Okay, so the last unit is different to the 3 because it covers light. Okay, so today we are going to look at unit number 4, visible light. So we are looking at unit number 4, visible light. This is on page 215 of your textbook. Now, visible light is broken down into 10 subsections. 10 subsections. Okay, and we are going to cover all of these subsections, and you can also see that these subsections, they also have little divisions, but we are going to cover everything in this unit 4. Okay, so unit 4, visible light. Okay, so now let's start on page 215 with section 4.1, and we will cover the light energy. Light energy is emitted from luminous objects, and light energy reflects off some surfaces and objects. Light energy is absorbed by certain surfaces, and light energy is reflected by transparent objects. So these 4 bullets are the characteristics of light energy. Okay, if you are asked about the characteristics of the light energy, the first one is that light energy is emitted from luminous objects. Light energy reflects some surfaces and objects, and light surfaces is absorbed by certain surfaces, and light energy is reflected by transparent objects. So on the first point, what do they mean by luminous object? Luminous objects are objects that are giving out light, or are objects that are shining. For example, like your sun, it is shining. The stars, you have the candle, and we have the light bulb. So all these are luminous objects because they give out light, or either they are shining. And we are going to cover all these phenomena: reflection, absorption, and refraction. Okay, but you need to know these 4 characteristics of light. Luminous objects are light sources that radiate energy. Oh, now it's explained. Okay, luminous objects are light sources that radiates light energy. For example, the sun, the stars, candles, a glowing light bulb. And they say light energy is transferred by radiation. Okay, light energy is transferred by radiation, so you need to know that as well. Now we look at non-luminous objects, the objects that they don't produce the light, or they're not shining, but they light from the luminous objects. So non-luminous objects are not a source of light energy itself, but reflects the light of a luminous source. For example, the moon. We know that the moon is not shining, but it is bright because of the light that it gets from the sun. We have done this when we done the solar system in the previous grades. So those are non-luminous objects, and the examples are moon, which reflects the light of the sun, the planets, and all light reflecting objects are example of non-luminous objects. Okay, so we have the planets and the moon here as the examples. Then we look at what is propagation. Okay, so they say light moves in a straight line. Look at your own shadow in the sun. Okay, for example, here we see the shadow. The shadow lies in a straight line with the position of the sun. The fact that the light moves in a straight line can be demonstrated with a pinhole camera. It consists of a small container with a hole on the one side. Okay, so you need to know that light moves in a straight line. Light moves in a straight line. So we are going to see a short investigation to investigate the propagation of light in a straight line. So in this investigation that is on page 216, this is what we will need: a card box the size of a shoebox, aluminum foil, wax paper, adhesive tape, scissors, piece of cardboard, a pin, and a candle. Then we will be able to complete this investigation, but we will watch it on video and we will see how light moves in a straight line and the demonstration of propagation of light in a straight line. Okay, which means it's the movement of light in a straight line. Okay, we will now start with our experiment.
Pinhole camera. The principle of pinhole camera is based on rectilinear propagation of light, that is, light travels in a straight line. Let us learn the working and construction of pinhole camera. The image formed by a pinhole camera is inverted and smaller in size when compared to the original object. Pinhole cameras are cheap and simple to make. Let's learn how to make a pinhole camera. Take two rectangular boxes that fit into one another without leaving any gap. Make a small hole in the larger box at the center. On the opposite side of the small box, cut from the middle a square of about 5 to 6 centimeters. Cover this opening with tracing paper. Finally, slide the smaller box into the larger box, ensuring that the pinhole and the tracing paper are in line with one another. Keep a lighted candle at a distance of 50 centimeters from pinhole camera. Now, look at the candle through the hole of pinhole camera. You can see the inverted image of a candle on the screen of the camera. Slide the smaller box to adjust the focus so that you can capture the clear image of a candle. Now, let us see what are observations of the image formed in the pinhole camera. Number 1. Image of a candle formed is diminished in size. Number 2. Image of a candle formed is inverted. Number 3. Image of a candle formed has color. Let us see how image was formed. A light ray from top of candle A falls on the tracing paper at A1. After passing through the pinhole O, a ray from the bottom of candle B falls on B1. Similarly, rays from the candle fall on the tracing paper after passing through the pinhole. Together, these points of light make up an image of a candle. You can see an inverted image of B1, A1 of a candle.
So the way they made the pinhole camera in the video is a little bit different than our the method that is in our textbook. However, the working principle is exactly the same. So please try this and see if it works at home. Okay, and after doing that, let's just go straight to the bottom of page 217 and get to the explanation now. And they say that, explaining what we have just watched, light that moves through the pinhole shines on a photographic film, which is the wax paper that we have put. It shines on a photographic film direct across from the side where the hole is. Light moves in a straight line through the dark container and forms an upside down image of the candle object on the film, and we see through the different rays of the bottom of the candle and the flame part of the candle. How is the image inverted or turned upside down? When you move the camera further away, this is important and it was not shown in the video, but you need to know this. So if you move the camera further away from the candle, the image that forms on the film becomes larger. Okay, so if you move the camera a little bit away, you put more distance, the image becomes larger. With a bigger hole, if you make a bigger hole, the image is brighter because more light comes in through the hole, but the outside lines are not sharp. With a smaller hole, the image is dimmer, but it is sharply outlined. So what are the properties of the image that is formed by the pinhole camera? We've learned that the image is inverted, the image is real, and these are the two properties. The image is inverted and the image is real. Okay, it is as you see it. Okay, so with this covered, you are in a position now to cover the questions that are in page 217 based on the investigation, and you can also do exercise number 20 exercise 21 on page 218. Okay, thank you.